So yeah, if you haven't had a chance yet and you have a preference of what questions that I cover in today's class, please go to this URL right here. It's posted in the Q&A and in chat and whatnot, and vote for whichever problems you would like me to talk about. I do have a decent distribution, and maybe as you go through these things, you can try to classify what sections they come from. And you'll also probably notice that Chapter 6 in general, and especially if maybe you've already started to look at some of the past final exams and things like this, Chapter 6 is usually covered pretty lightly, I would say. You know, Chapter 5, usually there's representation, and Chapter 7, of course, with all those integration techniques. But like Chapter 6, thinking back on it, I mean, a lot of those facts, right? The derivative of e to the x is e to the x. We have hyperbolics, the derivative of sinh is cosh, stuff like that, right? You can kind of embed those naturally into Chapter 7 problems. And so quite often on final exams, I've seen not a whole lot of questions dedicated to Chapter 6. Maybe the one exception to that would be more like L'Hopital's rule stuff, because L'Hopital's rule gets used again in Chapter 11 when we deal with sequences. And also it sometimes comes up for improper integrals in like 7.8, stuff like that. So yeah, I would say L'Hopital's rule, but all of the other Chapter 6 stuff maybe more or less gets embedded very naturally into Chapter 7 material, for instance. So with that kind of overview, or kind of what my thoughts are, you know, about these early chapters 5 through 7, let me go ahead and peek and see what you guys have been voting for here. And it seems like the most popular question right now is example 6. So we'll go ahead and do example 6 first, and then we'll see what's in the lead after that. So example 6, the base of a solid S is a triangular region with these vertices. Cross sections perpendicular to the x-axis are squares, and we would like to calculate the volume. And so maybe the first thing I want to go ahead and do is just draw out the base, right? So it talks about a base, and we have 0, 0, 0, 1, and 2, 1. All right, so we have a nice triangular base right here. And I'll go ahead and shade this in for fun. And then it says perpendicular to the x-axis, we're appending squares. So perpendicular to the x-axis, that's going to be going in this direction right here. This also tells me that I'm going to be integrating with respect to x. Remember, whenever we are calculating out volume, we're going to be integrating area, but sometimes you integrate with respect to x, and sometimes you integrate with respect to y. And so this right here, what it tells me, you know, what it's perpendicular to, that tells me that I'm going to be integrating with respect to x. And the reason why is that if you were to write perpendicular to the x-axis, right, the x-axis has the equation y equals 0. That's the x-axis there. Y equals 0, right? We haven't moved up any, we haven't moved down any. And remember, the rule of thumb that we have is that we always integrate, you know, opposite to whatever this equation form is. And so since we see y equals 0, we're going to be integrating with respect to x. Now, of course, that's just the rule of thumb. Why that works, right? That maybe you want to go back to 5.2 and we talk a lot about, you know, why this works out to be the case, right? But basically what you're thinking about is that you're taking these tiny steps in the x direction, these little dx's, and seeing how things change. So that's maybe a quick explanation there. So, okay, each one of these we're appending squares. So if I had to think about this coming up out of the page, this would be hard for me to draw, but right, if I'm looking down on this, right, we're appending a square, right? And a square here and a square here, right? We're putting a lot of squares, and this is going to make some 3D solid that we're interested in calculating the volume for. All right, so the fact that we have squares, though, that means that, right, my area formula is going to be the area formula for squares. And the area formula for squares goes, well, you take whatever the length of the side of the square is, and you square it, and that's what gives you the area. And we have to get this in terms of x's, right? And so the length of the side of the square, maybe I should have kept the picture up for just a second longer, right? But these right here are going to be my various L's. And notice that they depend on where we are along this line, right? So this is going to be the side length of our squares. that we're appending to this base here. And if you have like a relatively small x, notice that this length here is considerably longer. Then as you get closer and closer to 2, right, the length here is going to be basically 0. So the big thing here is it seems to be the distance between these two curves here, right? Whatever this distance between this slanty line here is and this horizontal line, that distance between those two seems to be giving us the base length of our squares. So now that's kind of, right, our quest is to figure out how do we figure out that length between that, well, this is a vertical length in particular, between these two curves. And so having equations, of course, is very useful. This one up here is going to be y is equal to 1. Y is equal to 1. And that just comes from the fact that, right, we have the points 0, 1, and we have the point 2, 1, right? And if you were to find an equation of a straight line between those 2 points, you'll find that the equation, right, and you can solve the whole y equals mx plus b in general, and you'll get that your slope is 0 and your intercept is 1. And so you get y equals 1. It's a little bit more challenging, I suppose, to find the equation for this one right here. Maybe some of you are very good at this, right? You just kind of look at this and you say, well, the slope is a half, right? Because it takes me 2 steps over in order to go up 1. So rise versus run sort of deal. So 1/2 x, and my intercept is 0, right? That's where we're going through this y-axis here. So my y-intercept is 0. And so this right here will be the equation. But of course, you could also, go through and solve it with the whole y equals mx plus b sort of deal in full generality in order to get this equation as well. All right. And if we want to know the vertical distance between these two things, well, we're going to go ahead and subtract, right? Subtract the y values. And so I'm going to get that my length is going to be the bigger one, which is indeed 1 here. That's the bigger curve. It's higher up in the y spectrum, I suppose. And minus the smaller, which is 1/2 x. I'm not going to write the plus 0 here. And of course, let's be a little bit paranoid, right? Let's see if this is actually working out, right? Because if I go ahead and if I just, eyeball it, if I plug in x equals 0, I should get a length of 1. Does that work out for my equation? Plug in x equals 0, right? I haven't moved to the left or the right any. Do I get a length of 1? Yes. How about if I plug in 2, right? We already talked about if we have an x value of 2 here, the length ought to be 0. So if I plug in 2 for x, do I get a length of 0? And yes, that works out well. And so my length equation, and this is also good because, we're going to be integrating with respect to x, and so we need x's. My length equation is 1 minus half of x. And remember, for the area, we're going to take the length of our square and square it. And I guess also because we're integrating with respect to x, we can go ahead and specify our bounds, right? The smallest x value is 0, and the largest x value is 2. So before that, maybe this should have been like a's and b's or something like this. Some starting at any point, we just didn't know what they were yet. Okay, now that we have the setup, this is, quite often the most difficult bit. Now let's go ahead and do the evaluation. And so we're going to carefully FOIL this out. So we're going to have the firsts and the inners and the outers and the lasts. Oops. Getting ahead of myself, haven't integrated yet. Now we can go ahead and integrate, and I'll also try to skip a step and combine like terms here. So when I integrate with respect to x, the 1 becomes x. Let's see, this is going to be negative x, right? 1/2 is going to be a full negative x. And so when I integrate that, we're going to have x squared divided by 2. And then here we're going to have what? 1/12 x cubed. And again, we're integrating that from 0 to 1. If you plug in 0, you just get 0. And if you plug in 1, well, get this. And so let's see, we have 1/2 plus 1/12. And so let's multiply by 6 on top and bottom here. And we're going to have 7/12, I suppose, is my final answer. And that's not so great. because I did not list the correct answer there. Well, let me see. Maybe I made a mistake or someone. Oh, 0 to 2. Thank goodness. I was going to say, did I really mess this up when I was writing these answers? Maybe I did. 0 to 2. Thank you. And look, we were saved because, right, none of the above wasn't listed there too. All right. Take 2. Quite literally. 2 minus, let's see, 4 divided by 2 is going to be 2 plus 8/12. So these are going to perfectly cancel out. And then 8/12, right? We're going to have what? 2/3. There's going to cancel a little bit. So 2/3, the answer is going to be D. Thank you very much. All right. Any questions about this one here? Well, I popped up the Q&A. Why is Professor McComb standing in what looks like a basement? Yeah, I built a standing little desk thing here, and I am indeed standing in what is indeed my basement. Yeah. With a ping pong table and everything, and too many pieces of paper. Let's see, no raised hands yet. Any other things in the Q&A that we should talk about?
Yeah, this one asking is he's treating this question as a triangular prism and just found the volume manually.
So I don't think that this is a triangular prism. If you put it on its side, would it be a triangular pyramid? Well, no, it'd be like a square pyramid or something like this. So yeah, it's not a prism. I think so. It probably would end up being a pyramid, but you do have to be a little bit careful with these cross sections being squares and everything. I'm not sure if that's obvious necessarily that it is a pyramid. But yeah, so you couldn't, I can say for certain you shouldn't use the prism equation, but maybe you could get tricksy and use the a pyramid equation or something. Gabriel, you have the floor.
Oh, yes. Hello. I had a question. So I know that this is also like, I believe in chapter 5, if I'm not mistaken. And I know that like in that chapter we did solids of revolution, and like with that, you kind of, rotate some kind of like a face over some axes, and then it's kind of easy to see how it is, of course, like a 3D shape, and then you calculate volume. But
yeah,
with this problem, I'm kind of having trouble seeing how volume can be like, I guess, calculated at all. Like where's like the 3D, where's the like 3D in this like base?
Yeah, so maybe I'm skipping a step a bit here that I didn't actually draw the 3D solid.
Okay.
So if we go ahead and we draw XYZ space here, and we need to go out 2 in the X direction, up 1 in the Y direction. And if I'm going to try my best to kind of put this shape in this 3D space. So here's what the base looks like here when it's lying on the table. And then we have those lines that are perpendicular to the X-axis that look like this. And then to each one of those, right, we're appending a square.
Oh, I see.
That wasn't my most beautiful square, but so each one of these we append a square. And this is the thing that we're trying to find the volume of.
Okay. Yeah, because I was just having trouble visualizing how some kind of height of the face can be like determined from that. But like, since we have the length of the face there, then obviously it's a square as well. So its height will also be determined from its length. Okay, that makes a lot of sense. Yep.
Super.
Thank you.
Yeah, no problem. Okay, well, with that, let's go ahead and move on. Let's see. Right now, overwhelmingly, question 1 has taken the lead. So question 1 is kind of getting to this idea exactly with rotating. So this is another chapter 5 style question. This time we're calculating a volume by rotating something. And we have draw a picture, and then we're going to go ahead and set up and evaluate an integral that represents the volume. So find the volume of the solid generated by rotating the region in the XY plane in the first quadrant between a couple of curves. So let's go ahead and draw the square root curve, and y is equal to 2. So y is equal to 2 is maybe, we'll go ahead and put it there. Erase that. And so that's going to be our y is equal to 2. And let's see. It is in the first quadrant. So, I mean, I drew maybe this line a little bit too far to the left. I only really care about in the first quadrant. And let's see, first quadrant between these two curves, and we're going to do about the y-axis. So the only piece that's really between these two curves that's bounded here is going to be this piece right here, right? It's in the first quadrant and it's bounded by these two curves. And we're going to rotate this about the y-axis. So our axis of rotation is this bit right here. And we've also played this game where you rotate about like the x-axis or other, lines. But that's what this is going to look like. And let's see, we have the region, but it has to draw a picture of the solid. So let's go ahead and finish this up just by rotating this about the y-axis. It's going to look like kind of a spinning top sort of deal. So something like that. So that's the thing that we'd like to find, well, in part B anyway, integral representing the volume. So, okay, let's go ahead, and anytime you want to find volume, you're going to be integrating area. In this case, because we're rotating about the y-axis, and the y-axis has the equation x is equal to 0, right? So that means that we're going to be integrating with respect to y. So integrate, our area formula is going to be with respect to y. And you can see that if we take these small steps in the y direction and do these kind of small slices, from the picture here, you can see that we have solid disks, right? So my area formula is going to be just the area formula of a circle. We've also encountered sometimes where you have a hole in the middle, right? And then you don't have a solid disk, but rather you have one of these washers, right? And then you need to use like a washer method or whatnot. But this is nice because kind of our region butts right up against kind of our axis of rotation. And so we'll just have disks, which that tells me, right, that when I go and I do my area formula, because they're full disks, right, I can use the area equation for a circle, pi r squared. Again, we're integrating with respect to y, so my bounds need to be these y values. The smallest y value that's included in my region is going to be down here at y equals 0. And the largest y value included in my region is going to be, well, cut off by this y equals 2 line. So I can say already that we're going to be integrating from 0 to 2. The last question that we have to answer before we actually evaluate and all that good stuff, right? How do I figure out the radiuses with respect to y, right? The radiuses, I'll go ahead and draw them here. The radiuses are changing, right? The larger the y value we have, the bigger the radius is. And notice that these are some horizontal shifts, right? And so really we're trying to figure out what is the, if I look at just the region, right? I have my x equals 0 is kind of my small curve here. And my bigger curve is going to be, well, this thing right here, right, which was given by y is equal to root x. But if I want to solve this for x equals, right, this is going to be x is equal to y squared. Since I have a couple of x values now, x equals and x equals, if we just subtract the two, that will give us the horizontal difference, right? This horizontal distance between these two curves. So the bigger one is the x equals y squared, and the smaller one is x equals 0. So this right here is going to be my radius. The difference between these will give us that distance. And of course we can check, right? If you plug in y equals 0, this suggests that our radius ought to be 0. If we plug in y is equal to 2, way up here at the top, this suggests that our radius is 4, right? And of course, it would take a little bit, but we know that, maybe I'll move this stuff over here, that, right, if you go a distance of 4, right, the square root of 4 is 2. So that's when it's going to be intersecting y equals 2 up here. And so, yes, this does seem to be all working out. So our radius is just given by y squared. So let's go ahead and swap that in. 0 to 2 pi and y squared being squared, right, because it's r squared there. And we're integrating with respect to y. So we've set up, that's usually the most difficult bit. Now let's go ahead and evaluate this fairly fast. I'm going to try to skip a step here. And so y squared squared is going to be y to the 4th. And when I integrate that, I need to raise my power by 1 to get to y to the 5th and divide by that new exponent. And then we're going to evaluate this from 0 to 2, not 1, like I made the mistake last time. And when you take 2 and you raise it to the 5th power, that's going to be 32. So 32 pi, divide that by 5. And this right here will be our volume. There we go. All right. Anito, you had your hand raised. What's going on?
Just a hypothetical question. So if our curve was, shifted 1 unit to the left or to the right, would our, instead of our x equals 0, would that be x equals 1 or -1 instead? And then we have to subtract y squared from that number.
I think you would still, I mean, so long as it doesn't surpass like the y squared in this hypothetical, you would still do y squared minus whatever that value is. So y squared minus -1.
Okay.
But you would also need to change your axis of rotation. So there's a couple things that would need to change, but yes.
Okay, for sure.
Yeah, that would work out.
Thank you.
Good. Yeah. Let's see. Any questions in the Q&A, Yuan?
Why didn't we subtract the 2?
Why did we subtract the 2?
I guess for the radius, I don't exactly know.
Yeah, I don't think we subtracted any 2s throughout this. We subtracted 0. And it's just because we had we're looking for horizontal distance, right? So we want to subtract a couple of x values, right? So you can think about this as right? We have a couple of curves that are solved for x. So this is maybe x2 and this is x1. And when you subtract those, right, that's going to give you the horizontal distance because it's a difference of x values. And that's, after all, what we wanted in order to find these radiuses here. We wanted to have that horizontal distance. So we wanted to subtract x values. And that's why that worked out. All right, good. Let's go ahead and take a look.
Okay, I think there's another question. Is there any generous tips on dealing with this revolution problem?
I mean, I feel like we touched on a few of them, right? I think that, even in D2L, where it may not necessarily say that you have to draw a picture or that it'll be graded, your picture will be graded. I think that drawing a picture is very useful because then you can see where the radiuses are. We've also touched on things like the rule of thumb, right? Given your axis of rotation. So in this case, our axis of rotation was the y-axis. And we knew that we were going to be integrating with respect to y because of that. And so, yeah, there's a couple of rules of thumb, but also I just want to remind everyone that all of our old class videos are still posted on D2L. And so if you go into the course navigator, which is on the drop down list there, that you can get all of our old videos on any of the topics, including 5.2. So if you have identified that 5.2 is something that you would like to study more in preparations for the final, I would maybe recommend go back and rewatch our class video. And hopefully things, click from that. And if not, then maybe go back even a little bit farther and watch the pre-class video stuff, just as a good review. Good. Well, example 10 has shut out in front now. So we'll take a look at example 10. Yes. So example 10 is one of these. This is actually a chapter 6 style question, like 6.5 or so, right? Where we had some applications, right? This was right after we had exponentials and whatnot. And of course, one of the main things that these get used for are exponential growth. And you'll see that there's no calculus here. We won't take any derivatives or integrals or whatnot, but I have actually seen these show up on, the final decently often anyway. And so, yeah, so at time 0, we have some bacteria culture with 100 cells. It's growing at a rate proportional to its size. So remember, that's one of the key things from this 6.5 section, is that this is some code phrase, right? Essentially, growing at a rate proportional to your size is really, is really saying something about a differential equation, right? Remember, this was 6.5 was also in a section along with 9.3, where we solve these differential equations, separable differential equations, kind of similar to number 9 here. And so that setup right here essentially gave us the fact that this is going to be exponential. And of course, we know a lot of bacterial cultures and whatnot have exponential models. And so it also goes on to say, right at time 1 hour, we have 200 cells. And the question is, well, when will you have 300 cells? So we need to remember, or you can drive this again using, the separable differential equation and whatnot. But I would probably recommend, in fact, yeah, so we'll use P for population, is equal to some initial population and e to the kt. So this is kind of your generic exponential formula. We know at time 0, there's 100 cells. So this is saying something about our initial population. We know that at 1 hour, we have 200 cells. So let's go ahead and plug in 1 hour. That's a time value. So I'm going to plug in 1 there, and we're going to have a population of 200 cells. And so we can go ahead and divide and take a natural log on both sides. And we'll get our k as the natural log of 2. So right now we have a full function, right, with all the bells and whistles, 100 e to the natural log of 2 times t. Be careful here. This e and this natural log of 2 don't just cancel exactly. This times t is kind of ruining things a little bit. So be wary about trying to cancel these things when you have extra coefficients running about, I suppose. But still, we can answer the question, when will the bacteria culture have 300 cells? So we're going to set this up. 300 is equal to 100 e to the natural log of 2 times t. And we're going to be able to solve for t, right? The question again is when? When will the bacteria have 300 cells? So we're going to answer this with a time value, t equals something or other. So we'll go ahead and divide by 100 on both sides. We'll take the natural log on both sides. And now this natural log will cancel with this e here, and we're just going to be left with whatever's on the inside. And now we can go ahead and divide in order to solve for t by itself. So the natural log of 3 divided by the natural log of 2. So natural log of 3 divided by the natural log of 2. Be careful also about coming up with, your own formulas and whatnots or ways to simplify this. This, for instance, and it's nice we have a TI-30 calculator, right? So you can verify, but this is not equal to the natural log of 3 divided by 2. I know it's tempting to kind of factor the natural log out to some extent, but that sadly is not a property of natural logs, and this will yield the wrong answer. And so, yeah, C is not equivalent to D. And you can plug that into your calculator and verify that you do indeed get different answers. So just this is the correct answer, not the other one. Excellent. Ian, you have your hand raised. What's going on?
Okay, so I was just wondering, could it also be just 3/2?
The natural log is important here. It's not going to be 3/2, and that's going to have to deal with the fact that we have an exponential growth. Maybe if you had something more like linear growth, that would be true, right? But this is going to be actually ramping up, and you'll get to 300 actually faster than 1.5 hours.
Okay, thank you.
Yeah, definitely. Any questions in the Q&A, Yuan?
Yeah, there's one which is asking, when calculating when it will be 300, can we start from 200 and add the time it takes from 100 to 200 to yeah. From 100 to 2, I'm not sure what it's talking about.
Yeah, you
Yeah.
could, but then you would need to use some weird property at the end in order to see that this is actually the same thing, right? I don't think it'll be nearly as obvious that your answer is the same as the natural log of 3 divided by the natural log of 2. So yes, it's possible. And especially with a calculator, because you'll be able to plug this into your calculator, right, whatever your answer is, and then also plug in all of these answers over here into the calculator, and right, only one of them will have the same decimal equivalency. And so you'll just choose that one. So yeah, it would work out, but you wouldn't be able to stare at it and see that they're maybe equivalent so fast. Good. All right, so let's go ahead and take a look here. It seems like example 8 is in the lead right now of the ones that we haven't done. Example 8. All right, so yeah, this one is relatively nice once you know kind of where to look and what you're doing. This one here, right, the question is how much work? So this is a 5.4 style question. And remember, I think the only thing listed on the formula sheet is that if you want work, you need to integrate the force function. And so in particular, this is nice to us. It tells us a force function. 6x is our force function. And so we're just going to go ahead and set that up. And it says we're moving the particle from x equals 1 to x equals 3. So we're going to go ahead and just plug these things in. X equals 1 and x equals 3 are going to be our bounds. That's actually what we're, moving the particle and seeing how much work is done on that span there. And so we can integrate 3x squared, evaluate from 1 to 3. So let's see, if I plug in 3 and square it, I'm going to get 9. If I plug in 1 and square it, I'm going to get 1. So 3 times 8 is going to be 24, because this is pounds and these were feet, right? This is going to be foot pounds. So the answer here is A. All right. With that, seems like example 7 is
There's
next.
a question about this one.
Yeah, go for it.
Yeah.
Sorry.
Yeah, so how would you find the force function if it wasn't given?
Yeah, so I would recommend, right, in the 5.4 lesson that we had, we kind of broke down 3 levels to some extent of force questions or work questions from force. The first one is either the force function is given to you or Hooke's law style problems, right, where the force function is just kx, right? And so you can see that this is, well, it doesn't bring up a spring or anything like that. Or any natural length, but you can see that this is a kx sort of force function. So that's the first one. The second level of force questions that we had were ones where you were lifting cable or rope, or you saw stuff like, maybe you had stuff at the end of them like leaky buckets or elevator cars or whatnot. So all that sort of stuff. That's maybe the second level of work question. And then finally, the third level of work question is when you're pumping liquid. And I think that's where we're going next, actually. Yeah, as example number 7. And example number 7 here is exactly one of these pumping liquid style questions, right? So still we're asking about how much work is required. And in this case, we're going to be pumping liquid out of a tank. So this is kind of the third level, and quite often the most difficult, just because you have to set up a rather difficult force function. And this is one of the things that's not on the formula sheet, but you should revisit and have this memorized, I would say. Whenever you have a force function when you're pumping liquid, remember it relies on the density. It relies on the distance that you need to pump the liquid, and it relies on the cross-sectional area at each height. So this right here is a formula that I would recommend having memorized from 5.4, even though it's not on the formula sheet. And we're going to be integrating that from some A to B here, right? So this is a starting and ending heights, right? For in terms of y values here. So I think I wrote these in the order that I believe they're usually easiest to find. So for instance, density is always just kind of specified for us. So in this case, our sigma value, our density, sometimes this is denoted in some textbooks as a delta. But I think our textbook uses sigma here for density. So that's 10. Let's see. Let's also visualize this. I have to read the rest of the question. We have a circular tank containing liquid at this density, has a radius of 2 feet, and the sides are 5 feet high. So, okay, we have a nice circular tank, maybe like a above ground swimming pool or something like that. Radius of 2 feet. The sides are 5 feet high, and the liquid is only to a depth of 4 feet. So use darker blue for, okay, our actual liquids here, and that only goes to 4 feet high. And the question is, we want to pump all the liquid out over the top of the tank. So this is where, for our distance, this is going to be 5 minus whatever height the water is already at. So remember, you're taking these little cross sections in the y direction, and you need to pump it up, right? If you have a speck of water that's at height 0 or y equals 0, well, in order to pump that up to the top of the tank and over, right, you need to pump that a total of 5 feet, right? So 5 minus 0 would work. If you have a speck of water at the top, right, well, you only need to pump it 1 foot, right? So again, here, 5 minus 4 will give you the 1 foot. So that's the 5 minus y for our distance. And then usually the cross-sectional area has the possibility of being the most difficult thing. In this case, it's actually quite nice. So this is, right, we saw maybe more difficult problems, for instance, in web work and whatnot. But in this case, right, at each one of these heights, we just have a constant circle. And when I say constant, I really mean that the radius is constant. It's not changing or anything. But we saw cases like, for instance, if you have cones, right, then at each height, the radius of the circle is actually changing, right? And it's getting bigger as you have a larger y value. So that may be, maybe the worst case scenario that you may want to review. If it's still a little bit hazy, usually it has something to do with similar triangles, right? And relating stuff that way. But in this case, all of those areas are the same, no matter what the y value is. So it's just pi r squared. And so our radius is specified as 2. And so, yeah, pi 2 squared. So pi times 4 there. And last thing about this for our setup here is that you always integrate where there is actually water. Remember, kind of your bounds for your integral is specifying where you're actually doing the pumping, where you're actually applying the force, or once you add it all up, right, the work. And so we're going to be integrating from 0 to 4, but a common mistake that I sometimes see is that folks integrate from 0 to 5, right? They pretend that there's water here at the very top. My picture's now completely ruined, but they pretend that there's water up here and they need to pump that water out as well. But actually, right, there is no water there. You don't need to do any pumping there. And so the only work that needs to be done is pumping the water that exists between 0 feet and 4 feet. If you do 0 to 5, you'll get the wrong answer, sadly. So, all right, let's go ahead. And with this, we can go ahead and evaluate. The 2 squared is going to make 4, and the 10 is going to bring 40 out. I can also bring out the pi, right? So 40 pi. And now I'm going to be integrating from 0 to 4 of 5 minus y dy. So once you have the setup, the integral is not so bad. Integrating 5, we get 5y. Integrating y, we're going to get y squared divided by 2. And again, we need to evaluate that from 0 to 4. So let's see. When I plug in 4 for there, we get 5 times 4 is 20. And then 4 squared is 16 divided by 2 is going to be 8. And so that's going to be 12. So 40 times pi times 12. And so that's what, 480? 480 pi's. So the answer here would be D. All right. So that is a more difficult style work question, right? Where you have to set up all of these things, the density, the distance, the cross-sectional area, all that sort of stuff. Michael, you had your hand raised. You have the floor.
Thank you. So why would it be from 0 to 4 and not from 0 to 5? I'm confused.
So yeah, if there was water all the way up to the very top, right? Because in this case, it just says that the depth of the liquid is 4 feet. This is where you need to apply your force. This is where you need to, once you've added it all up, do the work in order to pump the liquid out. If you did 0 to 5, then you'd be pumping liquid also from the very top here. But notice that there's no liquid here.
Oh,
And so if you, do go from 0 to 5, you'll get the wrong answer, unfortunately, just because, again, there's no actual liquid there to pump.
so basically what you're saying is that depth equals like the initial height and that equals like the B value.
Depth equals the initial height, which equals the B value. In this problem, yes.
Okay.
All right, great. Yep. Good. Oh, a few more raised hands here. Chris, you have the floor.
Oh, hello, Mr. Ryan. Can you hear me?
Yeah, sure can.
Yeah. So, Mr. Ryan, I've got like question about this. So how did you get, first of all, 4 right here, because it says 4 and then it says like radius of 2 here. So I got kind of confused there, and I was just wondering, why is it like 5 minus y, why is it set up that way, So those
Yeah.
are my questions.
And so, I mean, I certainly agree with your assessment here that, right, these problems throw a lot of numbers at us, right?
Mhm.
We've got a
Right.
10, we've got a 2, we've got a 5, we've got a 4, right? They throw a lot of numbers at us. And so definitely the first thing that you really need to do is spend some time with the problem, reading it. And notice it wasn't long before we sketched a picture, right? Translating all of those numbers there and seeing how they actually fit together. Right. And so we saw that the tank was 5 feet tall. The water only goes up to a height of 4 feet. And now I kind of ruined it here, but I also had this radius of 2 feet here. And so I think that drawing a picture whenever possible really helps to see how all of these things fit together. You also see that kind of the odd man out there, the 10 pounds per cubic foot, doesn't really have a place here. I mean, you could write the density over here if you'd like, 10 pounds per cubic foot. But that's really, you plug it into the equation, right? But it doesn't really fit in the picture so well. So that's maybe the answer to your first question there. You also, sprinkled a few extra questions about like, why is your distance 5 minus y, right? And we talked a little bit about that kind of depending on where your water is, whether it's at a height of y equals 0 or if it's at a height of y equals 4. That changes the distance that you actually have to pump it in order to get to that top level here. And so notice that it always kind of fits in this form, some constant minus y, right? All of the distance formulas. And maybe I would definitely recommend go back and rewatch our class videos and maybe also peek at some of the web work homework, because that'll kind of hopefully you've saved your notes from the web work homework. You'll see that kind of time and time again, all of the distance formulas for these liquid pumping problems are always some number minus y. And so, yeah, I think that those are the big things that you mentioned. Does that all make sense?
Mm-hmm.
Super.
Yeah. Thank you, Ryan.
Yeah, of course. Good. And maybe one more question here from folks with raised hands, then we'll see what's going on in the Q&A. Jeff, you have the floor.
Thank you, Professor. Since the work would be the same, presumably, if this was an in-ground pool, can
Yes.
we still use the 5 minus y if we're more comfortable with that than starting at 0 and going to -5 for our distance?
Yeah, definitely.
Okay, thank you.
Yep. If you were to integrate from, like -5 to -1, you would have to change things a little bit for your distance, but yeah, that would all work out perfectly fine.
Thank you.
Yep. Good. Well, any questions in the Q&A that we should talk about?
Yeah, there are two. One is a specific one, which is asking the integral of force was work. But here we have something like force times distance.
When you collect all the units here, this ends up being the units are pounds, right? Because this is pounds per cubic foot. Per cubic foot is our density. The distance is going to be in feet, and the area is going to be in square feet. And so all of that together gives us a unit of pounds. And so this right here is actually force. So we are integrating force to get work. Good. So that was one. You said there was another?
Yeah, this general one, which is asking, can you give a summary of the three formulas of work in different three kinds of scenario?
So we have the one here. The other one would be Hooke's law. So force is equal to kx for Hooke's law. And then for the lifting cable one, remember those are a little bit more ad hoc, right? And quite often we drew a lot of pictures in class and we said, well, if you haven't lifted any of the rope yet, how much force is being applied? If you lift 1 foot of the rope, how much force is being applied? And so you kind of have to figure out the formula by doing a little bit of guess and check sort of deal. So there's not a set formula that I can give for that one. Yeah. All right. The question with the most votes right now is example 9. And so maybe this will be the last one that we do for today. And remember, next time we're going to be reviewing some of the later stuff, chapters 11, 10, 8 sort of deal. So these are all separable differential equations. So we need to go ahead and separate, get all of our x's on one side, all of our y's on the other. And so I'm going to go ahead and write this y times dy is equal to 1 over x dx. Again, kind of the important thing is having both your dy and your dx in the numerator here. So that'll kind of determine what sides you want to get these things on. Then we're going to integrate. So when I integrate our y's, we get y squared divided by 2. And when I integrate here, we have the natural log of the absolute value of x. Now, usually we combine our constants of integration just for one constant here. So I'm going to put the plus c on the right-hand side. And so lastly, we're going to go ahead and solve for y. So I'm going to have y squared is equal to 2 natural log of the absolute value of x plus 2 times a constant is still a constant. It's a different constant technically. So maybe if you want to do c prime or c tilde or something like that, that's fine. But otherwise, I'm just going to leave it as c. And then I'm going to take a square root. And remember, whenever you take a square root, you have to have plus or minus. And this is where we get into our initial condition here, right? We would like that when you plug in 1, you get out -2. So that actually tells me right now, right, if my output needs to be negative, well, then I'm going to need the negative square root. If I have the positive square root, right, square roots are only going to spit out positive numbers. So the only way you can get negatives is if you include the negative square root. So I'm going to actually need the negative one here. And then let's see, in order to solve for our c value, we need to plug in 1. And again, we're trying to get out -2. So -2 when I plug in 1. And so the natural log of 1 is 0. And we can go ahead and square both sides. And this is going to give me c is equal to 4. And so it looks like E is the correct answer here. We have the negative square root. Notice it looks like they've chosen a restricted domain where they're only plugging in positive x's. That's fine. And we have the +4. So E is the correct answer there. All right. Well, thank you so much, everyone, for joining today. We'll stick around for a few one-on-one questions. But again, remember, next time we're going to be talking about review for the later half of the class, so chapter 11, 10, and 8. And then also, if you're interested in even more review after Wednesday's class, I'm going to be holding a review session on Friday, the 23rd from 4 to 5. We'll be using the same Zoom URL here. And if you would please, this is going to be a little bit more free form where you can propose questions that you'd like me to talk about. But if you would, just so I can take a look at them ahead of time, please let me know what they'll be by filling out the form there.
Will
All
it
right.
be recorded?
Will this be recorded? I'm not opposed to it. So yeah, I'm happy to record it and post it. I'll post it on D2L and make a little announcement once it's there. Good. All right.